Well, hello everybody, and thanks for joining, and a very warm welcome wherever you may be today to our fibUK conference on developments in structural concrete innovations for sustainability and low carbon design. I'm Chris Hendy. I'm head of bridge engineering at Atkins. I'm the current chair of fibUK, and I'll be chairing the conference today. If you would like any more information about fibUK though and the benefits of becoming a member, then please do reach out to either me or to the institution. The institution provides all the committee management for fibUK. So if you want to do that, the email address is shown on the slide here. So you might want to just take a screen capture before we move on if you do indeed want to have a chat. So just before we start sort of proper, just a few quick bits of information for everybody. So you can ask a question via the Ask a Question box that's in the bottom right of your screen, and obviously you can do that at any time. No need to wait until the end of a presentation. In fact, it'd be very helpful if you put it through as soon as you think of it, and I'll pass on your questions to the speakers during the Q&A sessions. You've got access to all of the speaker profiles. They're underneath the slide, so I shan't read those out in full for introduction, but I will say just a few words of introduction, if nothing else, just to give some time for sharing screen. If you do have any technical issues with the audio or the slides during the webinar, then first thing is just please check your connection. So there's a link directly under the slides to help you do that. You can also chat live with the technical support via that link if you do need to. But typically I understand from experience using Workcast before, generally the best thing to do is simply to refresh your browser or just log back out and back in again. The institution and all of our presenters today, everyone's done their best to try to sort of check up and make sure we're not infringing any copyright permissions at all for the materials that are going to be used. But in the course of the presentation, if you do think that you're the owner of something that's up on screen and you haven't been asked about it, then please do contact the institution if you feel the need to, and we will either get it acknowledged before this is distributed or get it removed from the content. So this is actually our 10th development in structural concrete event that we've run now consecutively, but it's the third online version that we've done in a row. And FIB's overarching goal is to be a bridge between research and practice. So that's precisely what we're trying to do really with the conference today, focus on research and practice. And the conference is going to be split into 3 parts within 2 sessions. So the first session will be research. We'll have 2 research presentations. We will hear about some current research topics that have got the potential to transition into practice or improve or transform low carbon design. We're then going to hear about a new FIB bulletin, which captures proven research and best practice and makes that accessible for all of our sort of practitioners to implement in design. And then finally, at the end of the conference, we will hear about 2 projects that have addressed sustainability and low carbon design in real practical ways. So what I'm going to do is I'm going to stop sharing the screen right at this point so I can give our first presenter, Janet, time to get into position. So what we're going to have, the format for today is that we're going to hear from all of the speakers in each session. Then we'll have 10 to 15 minutes of questions before we move on to the next section or a break. So with that, I think we can just get going. So I will introduce our first speaker. Our first speaker is Dr. Janet Lees. So Janet leads the Concrete Infrastructure Research Group within the Civil Engineering Division at Cambridge. And she was awarded an EPSRC Established Career Fellowship in 2017. And Janet is going to be presenting on levers for concrete CO2 impact reduction. So Janet, over to you.
Thank you very much, Chris. Yes, so I'm Janet Lees. Because you can't see me at the moment, that's what I look like in real life. As Chris mentioned, my group is interested in concrete, in particular the CO2 impact of concrete, lifetime extension of existing structures, and tailored reinforced concrete infrastructure, and we'll touch on a few of these topics today. So just as a quick recap, the CO2 impact of cement is responsible for 5 to 7% of CO2 emissions, and that's connected to the fact that we use very large volumes of it, and approximately 1,000 kilograms of cement is about 860 kilograms CO2e. The other thing, by way of introduction, is about concrete. I'm going to use the term as a single term, but actually it covers a great many materials with an infinite number of possibilities, different cementitious binders, mixed proportions, aggregates, and processing. And again, these will be threads through my presentation today. So if I look at the broad categories of strategies for CO2 impact reduction of concrete, I categorize them into two broadly. One is emit less CO2. So this comes under the category of, well, don't build if you don't need to, reuse, recycle, production savings, and material savings. And then the second strand is dealing with the emitted CO2 through, in effect, carbon capture and other means. So if I map that sort of umbrella classification onto some recent publications, this is the Mineral Products Association route map, and again, there'll be people on the call who can expand on this if required. Broadly speaking, the indirect emissions from decarbonized electricity, transport, low carbon concretes and cements, fuel switching, and thermal mass, I would put in the category of emit less, and then deal with emitted CO2 would come into the carbon capture, storage, and things like carbonation. If I look at another example of the low carbon concrete route map published through the ICE, then again, the kind of defining and benchmarking, the using concrete terms and aspects of making concrete are about emitting less, and the sequestration, capture and use is about dealing with CO2. So within that framework, the particular strand I'd like to pick up on for the rest of the talk is in the category of emit less CO2, and in particular material savings. So if we think about what we can do by means of material savings, one thing is to look at materials with lower CO2 intensity. The other is to look for higher efficiency, and therefore, in fact, if we can use lower volumes and connected to that, reduce consumption. I think the point I'd like to start with, though, is our options within this space are intrinsically connected with placement. And so as a review of placement options, there's really two ends of the spectrum, that at one end we have form structures and at the other end free form structures. If I think about form structures, this would be conventional, have some sort of form that we cast the wet concrete into. Free form would be things like 3D printing, where you see these amazing impressions of residential houses that could be generated using concrete 3D printing. But I think what's very useful to highlight is that there's a whole spectrum in between the formed and the free form, and indeed a lot of research happening within that spectrum. If we look on the left-hand image here, this is a waffle slab, which again is an optimized structure in many ways, and but now with circular holes to allow for services to route through. And then there's also active research, for example, my colleague, Professor John Orr here at Cambridge, looking at fabric formwork, where the fabric turns into the shape of the actual structure itself and allows for lowering carbon embodied energy. If we then look at something that has a form, but is also relying on the concrete rheology to some extent and setting, we look at slip forming. So fairly common in the left-hand slide for concrete cores, whereby the shutters lift as the construction progresses. But then there's also work done in this whole space of smart dynamic casting, whereby the slip form is actually moved while the concrete has not yet hardened to create different geometric forms within a sort of semi-slip form system. We then have sprayed concrete, which typically is on a surface of one side that is formed, and again, quite a common technique. But equally, there's work done at Stuttgart now looking at multiple nozzles spraying and using different materials through these two nozzles to, in effect, look at lighter weight particle distributions such that the whole material form can match the performance requirements and therefore, again, reduce weight and embodied energy. And then at the final spectrum of the free form, we have concrete 3D printing, which is the image on the right. I was trying to look at what would be the left-hand side picture for this slide in the sense of what's conventional 3D printing. and I wasn't quite sure about, but an interesting picture nonetheless, which is Urschel's wall building machine. Now, it's not actually 3D printing per se, it's something between, I guess, slip forming and controlled deposition, but this is an image of the patent. If you look, there's actually quite a good video on YouTube, so please do have a look at that subsequently. But in effect, what we have is, in effect, a hopper that the material goes in, fairly dry, lean mix. The shaping is done by those side wheels, and then it's tamped as they go along. And that dates from the 1940s. So that's quite an interesting history. And then again, in the whole 3D printing space, there's lots going on in terms of the concrete technology. So what I'd now like to do within this spectrum is think through the ideas of shape choices and material choices and how they interact with our placement methods. And broadly speaking, if I think of shape choices, that if we need to form them, they're more constrained. And then if I move to the right towards our freeform structure, the shape choices are less constrained. However, if we look at the material choices, potentially they move the other way, that if we have something that's freeform, the material needs to be self-supporting. It's very complicated rheology in terms of the material needs to be fluid enough to come out of the nozzle, but then it needs to gain enough strength quickly to support the next layer of concrete that is deposited on top of it. So the rheology and understanding of concrete is very important in that concept. If we look back at less constrained, to some extent, if we have shuttering, it forgives a great many ills in that we can make the shapes we wish, and within that we have a wide range of fluidities and rheologies that can be accommodated. And why that matters is putting the CO2 lens on this is the implications of the material choices. So this is work by my colleague Ma Gimenez-Fernandez, and what she did was look initially vibrated concrete and self-compacting concrete. She looked through papers in the literature, looked at the mixed compositions, mapped this ESO2, plotted that on the vertical axis against the compressive strength that people measured for those cubes. So these are results from the literature. But you see, again, this comes back to the point I made at the outset, that there's a great large spread because of differences in constituent material, construction method, and target properties. And I think really a strong plug here is that even within our fairly conventional concretes, if we have good understanding of performance requirements, we can really push to have the lowest CO2 mix that would satisfy those. Another colleague of mine, André Brandt, then looked at papers that had related to 3D printed materials and generally find that the ECO2 of these materials are much higher, that they're 600 plus. And this is partly because it tends to be fairly small particle sizes, has this very challenging rheology I mentioned, and therefore that drives up the cement content. Equally with spray concrete, the ECO2 tends to be of 400 or above. So you see what's key in this is that when we're making placement choices, we're also making ECO2 choices for the materials that we use. So if we're thinking about 3D printed material, there may be a great many reasons why we want to do that. But on simply the volume, we need to, if we compare it with conventional concrete, make sure we save quite a lot of material in order to offset the fact that we've used quite a lot of carbon in the 3D printed material. So this brings me to the theme of the talk about levers for concrete CO2 impact reduction. And really the question I'll interrogate for the remainder of the time is, can you benefit from a wide range of materials, efficient placement, and lower volumes and higher efficiency, and reduce embodied carbon? And I'll talk through some levers on the shape choices and material choices that influence this. So as a start, I'm going to look at the more constrained and less constrained space in terms of the example that I give. And that example is work led by my colleague, Philipp Reinschdorfer, and what he looked at was a railway platform. So this is fairly conventional shape, using form, but accommodating a wide range of materials. And so what he explored is how well can we do in this space. So this particular platform has some applied loads as well as some soil backfill. So the performance requirements about the loads it must sustain. And then what he did when he looked at material options is he considered steel, carbon fiber reinforced polymers, and glass fiber reinforced polymers. And he also considered two concretes, one a conventional concrete and two is a low alkali concrete. Now, why low alkali concrete came into the mix, excuse the pun, was that if we're using non-ferrous materials, potentially we don't need the high alkalis, the protection for the steel embedded, and so hence that allows maybe more opportunities about other types of concretes that can be used in conjunction with FRPs. So the performance criteria, he looked at ultimate limit state, flexural capacity, deflection control, serviceability limit state, stress limitations, and crack width control. And the key thing in this is he also looked at the global warming potential. So that was his measure of CO2. And so if we look at plots of concrete depth versus reinforcement area, what he did, so the vertical axis is depth. So this in effect is how the thickness of that retaining wall. And in effect, if we come down on this axis, we're using less concrete. If we go up on this axis, we're using more concrete. The horizontal axis is the area of reinforcement. So again, if we're going to my right on this, in effect, we're using more reinforcement areas. So what he did is he looked at all the combinations of D and AF and mapped out the boundaries, in effect, for the limits to satisfy his performance criteria, so the USLS and SLS conditions. And that gave a control line which determined a feasible area of combinations that would meet the performance requirement. But what then he did, if we look at the right axis on this plot, which is the GWP total, is he was then able to find the lowest GWP amongst these solutions. And so what we're looking for is a low value on that right-hand axis, and it's the combination of D and the AF that gives it. So he did that for the steel, he did that for the carbon fiber reinforced polymer, and he did that for glass fiber reinforced polymer. What he was then able to do is find the total GWP for that optimum solution per se, and we found that steel was 29.2 and approximately 10% lower through CFRP and GFRP. Now I should add that the cost isn't shown on here. Philip also looked at cost, so if you're interested, look at the paper, but in fact the FRP was more expensive in terms of the solution. However, if we now open up the possibility to use a concrete with a 40% reduced GWP, the low alkali concrete that was defined, we see that there's even greater savings that can be made. And so now the CFRP and GFRP solutions are 40% lower than an equivalent steel. And we haven't calculated that for the steel because, in fact, the low alkali wouldn't be compatible with the use of steel. So we start to see that how putting these materials together in clever ways can really look to reduce the impact. So that was a case where I looked at the shape choices being fairly open and material choices being less constrained. What if I use my lever now and say, okay, I'm willing to accept a bit more constraint on my materials? Where does that take me? And I'll use Philip's example to explore that. And one of the things we can do, my group has been working extensively in looking at functionally gated concrete, is the idea of using multiple concrete mix within a single element. And this allows us to tailor the concrete to the performance requirements. However, if we're going to layer one layer of concrete on top of the other, even if we keep the formwork, we do have to think about the fresh state stability and the compatibility of two mixes. So that's put a bit more constraint on the materials we can use, but actually the design space still remains very large. And then we can look at how that's connected to acceptable deviations in terms of the profiles between the two layers of concrete. So if I now say, let me put functionally graded concrete into the mix, we could go back to having a retaining wall of some sort. And actually, let's now consider the steel case. So if the steel we need to give good durability to, and it happens to be that this is in quite aggressive soil, potentially we could put in a high durability concrete, which is mostly connected to higher cement content, and then we could use a low durability concrete on the face that doesn't have such onerous durability requirement. So by considering a range of shapes and materials, we can start to scope many different combinations and mix and match appropriately for the given application. So if I then turn to a further example where I'm going to put my material choices back to be as unconstrained as possible, but I'm now going to put the lever on my shape choices. So I'm going to move them into a bit more constrained space. And I'd like to refer to work by another one of my colleagues. So this is work done by Michele Wintai-Mark. And what he did was he looked at beams. These are shear critical. They have no transverse steel in them. And the beam on the top is fairly conventional prismatic beam. But what he's done in the beam underneath is actually have a void within the structure. What he then did was load these in effect 3-point bending, and he tested them to failure. Now, in terms of the shape, actually the materials we used were fairly normal. They're concrete, a SEM1, 10 millimeter down gravel, slump about 100 millimeters. And this reinforcement was steel, so we've used very conventional materials. But the new thing in the shape was that we then needed this void former to create that void within his structure, but then we cast the concrete as normal. The results are quite remarkable. That this is a plot of shear force on the left-hand axis or the vertical axis and mid-spine deflection on the horizontal axis. And when these were tested to failure, these are plots of load versus displacement. We found that the prismatic beam failed in shear in a brittle way, but the beam with a voided center shape actually failed at least twice the applied load. So we had two things that are beneficial here. One was that we used a lower volume of concrete in the case because we didn't need any material in the void. And secondly, we've had an uplift in efficiency, which again, it means a greater performance for lower volume. So where I started from was to say, can we benefit from a wide range of materials, efficient placement, and lower volumes, higher efficiency, and reduced embodied carbon? And I hope the examples I've presented today will encourage us all to think that, yes, that is possible. And so that is indeed excellent outcome. As ever, I do very little, and the people around me do quite a lot. The people whose work I've specifically cited are named here, but actually my group in general work very collaboratively, so their thoughts and ideas permeate through this presentation as well. And our technical support team, I'd also like to acknowledge. We are funded through the EPSSC, and we also have a number of industry partners on this project. So thank you very much for your attention.
Thank you very much, Janet, for that. That's absolutely great. And the example of removing materials and strengthening is something I know that others have found, but it always is quite spectacular. And maybe we'll get some questions about that later on. Sorry, just for everybody, a few people have struggled with sound. Hopefully, the fact that you're listening to me now, it means that you've sorted out with test connection. Unfortunately, when I was going through the slides in the intro, I tried to suggest that would be a good thing, but clearly if your audio doesn't work, you wouldn't have heard, so I'm sorry about that. We have a few questions coming through, but please just a reminder, if you can submit your questions now, because we'll be taking Q&A after the next slot, that will be very helpful for facilitating that slot. So we're going to move on now. So our next speaker is Dr. Rachel Capon. Rachel joined the Mineral Products Association in 2017, where she's responsible for collecting and analysing environmental data from cement and concrete manufacturers and promoting the benefits of using concrete in designing sustainable and resilient buildings. And as you can see from the screen, Rachel will be presenting on modelling the UK carbonation of concrete emission sink. So over to you.
Thank you very much. Yeah, so as I said, I'm from the Rachel Capon from Mineral Products Association, and this is work that we have been doing for BEIS, for the UK government, on modelling the UK emission sink from the carbonation of concrete. This is a consortium project, so projects MPA have led the consortium, but we have other project partners. The key one is Ricardo, who are responsible for the whole of the UK greenhouse gas inventory. Also Heriot Watt University, Dr. Phil Renforth, Leading Edge, and the Concrete Society. So I'm sure you already know that about cement manufacture. Sorry, it's showing little. I hope the Alps aren't popping up for you. So cement's a man-made powder that, when mixed with water and aggregates, produces concrete, and we can divide the cement making process into two basic steps. Clinker is made in a kiln at temperatures of around 1,450 degrees C, and the key chemical reaction that's going on there is that the limestone is composed into free lime and to carbon dioxide. So the calcium carbonate breaks down into calcium oxide and CO2. Then once we've made the clinker, we cool it down and it's ground with other minerals to produce the powder we know as cement. So there are two sources of CO2 emissions from cement production. The first is the fuel emissions. So we're combusting fuels, coal or waste-derived fuels, tires, etc. These are all being combusted at high temperatures in the cement kiln, and they will produce CO2. That is about a third of the CO2 footprint from cement production, and that is reported in the National Greenhouse Gas Inventory Report. It's reported in the category 1A2F. Okay, I also showed you how the limestone is decomposed into calcium oxide and CO2. The calcination reaction that takes place in the kiln, that's in the UK, that's actually responsible for 2/3 of the total CO2 emissions from UK cement production, and that is reported in category 2A1 in the National Greenhouse Gas Inventory Report to the UNFCCC. Just a point to mention here, so we heard in the previous presentation the figure of cement and concrete being 5 to 8% of global emissions. In the UK, cement production is actually only 1.47% of the total UK emissions, so it is a much lower percentage of total emissions, which is partly because we have a mature market and lower demand than in other parts of the world. Okay, so recarbonation or carbonation of concrete, that can be, obviously the chemistry is a lot more, complicated than the simplification that I presented, but we can conceptually understand it as the naturally occurring reversal of the calcination reaction. So once the cement is incorporated into a concrete or another product such as mortar, it starts to reabsorb the carbon dioxide, and it's a permanent carbon sink. It's scientifically well established, and we do have established industry methodologies in EN 16757, the product category rules for concrete and concrete elements. We have established methodologies for calculating the carbonation for the purposes of EPDs and building life cycle assessments. Now, carbonation is also recognised by the IPCC, and there were some global carbonation estimates included in AR6. However, there isn't yet any IPCC methodological guidance for how countries could include it in their national greenhouse gas inventory reporting. Now, IVL, who are the Swedish Environmental Research Institute, have developed a calculation method working together with industry, and this aims to be compliant with the IPCC methodology. So it has 3 tiers of increasing complexity of calculation, which I'll come on to later. So just stepping back to give an understanding of how this fits into the greenhouse gas inventory. So under the Kyoto Protocol, Annex 1 parties, so the UK is an Annex 1 party, as are developed countries, they're required to submit a national inventory report of greenhouse gas emissions annually to the United Frameworks Convention on Climate Change. And there are reporting guidelines provided by the IPCC, which include greenhouse, and this covers the whole range of sectors, but they include the greenhouse gas emissions from cement manufacture that I already talked about. They also include greenhouse gas emission sinks. At the moment, the only sink that is included is a sink that comes from land use change and forestry. So, for example, the sequestration of carbon dioxide in timber. Now, recarbonation of concrete is also a greenhouse gas emission sink. As I said, it was considered but not included in the 2019 update of the IPCC reporting guidelines. At the same time, in 2018, IVL published a calculation methodology guidance. This was developed in collaboration with the cement industry globally, so CEM Bureau, GCCA, and the Portland Cement Association in the US were all involved. IVL are also the Swedish inventory agency, so they play the equivalent role to Ricardo in Sweden, and so they did include the Tier 1 calculation from their methodology. So the Tier 1 calculation, the carbonation sink, as a memo item in their inventory reports starting from 2020. Last year, MPA was commissioned by the UK government, by BEIS, which is the Department for Business, Energy and Industrial Strategy, to develop a model for the UK. The BEIS were very keen that we don't just develop a Tier 1 model, that we should actually develop a Tier 2 model, sorry, or at least Tier 2 model. So in terms of the IVL methodology for calculating the CO2 uptake in concrete, I said it's at 3 tiers. This concept of 3 tiers comes from the IPCC, that you have calculations at increasing levels of complexity. So Tier 1 is the lowest complexity, and that is based just on the calcination emissions for your cement clinker consumed nationally in that reporting year. So the carbonation sink is just taken as 23% of your calcination emissions that year, and this is the figure that was reported by Sweden, first reported in 2020. They had a carbonation sink of 297 kilotons of CO2 in 2018. The Tier 2 methodology introduces slightly more complexity. So you need to calculate the carbonation sink by considering how carbonation occurs in different concrete applications. You have to assume that the historic concrete consumption is relatively constant. You need annual data on cement consumption. You need data on the primary use of concrete. This you only need for 1 year, but you do need it to cover at least 5 different concrete use applications and at least 65% of your overall national cement consumption. And we calculate for each of these applications, you would need emission sink factors, which are based on the EN 16757 methodology and the concrete characteristics. For concrete entering the end of life or secondary use, the suggested CO2 uptake is between 10 and 30 grams of kilograms of CO2 per meter cubic of concrete. Okay, moving on, the IVL methodology suggests, that Tier 3 will be an advancement on this, but obviously if we're going to disaggregate the information further beyond Tier 2, then we're getting into the realm of advanced software models. So this is what an overview of what we've done in terms of the UK Tier 2 model development. So we started with a literature review by Dr. Phil Renforth at Heriot-Watt University. He recommended that we develop the Tier 2 methodology. We use it as a basis for the UK model for primary use concrete, and we follow EN 16757. He recommended that instead of using the factors given by IVL for the end of life, we should try and develop some more UK specific emission sink factors. And another area for future investigation that was flagged is that we have a lot of data on how quickly the carbonation front progresses. We have less data on how much CO2 is actually absorbed behind that carbonation front. So to develop the model, we've reviewed UK data sources. We need to identify annual activity data to input into the model. We need to identify appropriate concrete applications and calculate a sink emissions factor for each application. And we also need to calculate a sink emissions factor for concrete at the end of life and in secondary life. So the focus of the model is really on identifying the activity data and calculating emissions factors. It's not on improving our experimental and empirical knowledge of carbonation, although we have included some experimental data that MPA has access to. We've also done an uncertainty analysis in line with IPCC guidelines. I'm not going to talk about that today, and we've made recommendations for future work, and we are just finalising the project report, which will be published by BASE. So we've reviewed the data that is available for concrete in primary use. This falls into two categories. There's top-down data, so MPA collects industry data on cement consumption and cement sales by product type and regional cement sales. We don't really have top-down data on where the concrete goes and what applications it goes to in more detail. In terms of bottom-up data, there are quite a lot of data sets available. A big one is the ONS construction output, which is also broken down by sector and further by regional and subsectors. There's also commercial contract data from Glenigan and Barber and sector-specific data. So, for example, from the NHBC for housing. In terms of annual activity data, which we could use as an annual model input, we're going with the MPA. We've recommended the MPA data on cement consumption and cement sales by product type, which is top-down data. For the data on each application, we'll use the ONS construction output because that is already subdivided by sector. Also, we need to relate the top-down to the bottom-up data. So as part of our data analysis, we commissioned a market survey that was carried out by a company called Leading Edge to fill in these data gaps. So the primary use concrete applications we identified by a combination of data analysis, expert opinion, and the market survey. And the 5 choices that we made are composite frame buildings. So most commercial buildings fall into this category. Concrete frame buildings, so this includes high-rise residential buildings and hospitals. Masonry buildings, so most low-rise residential buildings are masonry, although there are some timber frame, which are not included in our study. Infrastructure projects, so energy, rail and roads, and mortar and merchant sales. So we have data on factory-made mortar, and we also have data on bag cement sales through builders merchants. So for each of these, we need to calculate the recarbonation CO2 uptake emission factor. And we've done this by using a representative case study for each application and following the EN 16757 methodology. So I'm not wanting to blind you with equations, and you're probably familiar with them, or some of you will be familiar with them already. So this is the methodology. So we assume a CEM1 with 95% cement clinker content. So then we have a maximum theoretical CO2 uptake of 0.49 kilograms of CO2 per kilogram of cement. The depth of carbonation is given by this equation. So the carbonation front moves through the concrete with the square root of time. K is in lookup tables. And also the CO2 uptake per meter squared of concrete surface behind that carbonation front is given by this equation. So DC is the degree of carbonation, which is also given in the lookup tables. And C is the cement or CEM1 content of the concrete. Now, ideally, this should be based on clinker content, but within the constraints of this project, we don't have that data available. We're using CEM1 as a proxy for cement clinker. If you've got concrete mixes which contain secondary cementitious materials, then the carbonation front progresses more rapidly, and so we have a slightly modified equation for the CO2 uptake per meter squared of concrete surface, where you've got this correction factor here, KK for SCM. And so these are the lookup tables that you will find in the annex to 16757. So you can see that the K factor for how quickly your carbonation front progresses depends both on the concrete strength and also its exposure, whether it's indoors, outdoors, sheltered from rain, buried, etc. And also the degree of carbonation behind the carbonation front depends on the exposure, with it being lower for indoor surfaces. This is for the secondary cementitious materials, so that the carbonation front just moves through the concrete a little bit more quickly. However, the overall CO2 uptake will be lower because we're only calculating the CO2 uptake on the basis of the CEM1 content, not on the basis of any SCMs. Okay, so the first primary use application that we considered is our composite frame office. So we've got a case study building, which is a 6-story office development. So you can see here the section through the floor zone. So most of the carbonation will take place on this upper surface above. So from the floor, because there's a void here, there won't be any carbonation on this metal surface here. There'll also be some carbonation in the foundations and the cores. For this one, we've actually considered 2 different concrete mixes for 1990 to 2000 and 2010 to 2020. That's because when we do the model for the greenhouse gas inventory, we provide data going back to 1990. We specifically had 2 mixes here because we wanted to understand what the carbonation that had occurred in the primary use life would be for concrete which is being demolished currently, and then we feed that into the end of life calculation, which I'll come on to. So for our office, we've got 2 different concrete specifications and minimum cement contents of the concrete. So you can see that there's more GGBS in the recent decades than in 1990 and 2000, when there would have been some GGBS in the substructure but not in the superstructure. So we get 2 different emission sink factors. So for the more recent decades, the CO2 uptake is 9.3 kilograms CO2 per meter cubed of concrete, but it's 12.5 kilograms of CO2 per meter cubed of concrete for the older structures. This is the second primary use type. This is concrete frame. So we've used a residential 6-story apartment block as our case studies. Again, we've got 2 slightly different concrete mixes. The reason for this is not just because, actually I'll come on to the reason later in the end of life, but again, it's to feed into the end of life calculation. The concrete frame residential is slightly different because most of the carbonation will be actually taking place on the exposed ceiling, whereas the floor is covered, so you won't be getting carbonation on the floor surface. And again, you get we've got more GGBS in the superstructure in the recent decades than historically. So the emission sink factor is slightly lower for recent decades, so it's 12.18 kilograms of CO2 per meter cubed of concrete, whereas going back to 1990 or 2000, it will be 14.1 kilograms of CO2 per meter cubed of concrete. moving on to the next two primary uses. So these are masonry and mortar. We've actually used the same case study prototype for these, which is a typical two-bed, two-story mid-terrace house. So in terms of masonry, we're looking at the carbonation within the concrete elements in the house. So these are lightweight aggregate blocks in the walls, both the external walls and the party walls. There's also some carbonation which will take place in the beam and block ground floor, in the strip foundations and the foundation blocks, and also the concrete roof tiles. We're also using the same case study prototype to model the carbonation of mortar in the party walls and the external cavity walls. For both these, there's a much higher emission sink factors because there's much more carbonation. In terms of the masonry, the lightweight aggregate blocks in the walls will carbonate all the way through within the service life of the building, as will the concrete roof tiles. You won't have the carbonation from progressing all the way through the foundations or the beam and block ground floor. And the mortar, we've shown that will carbonate through the entire depth within the service life of the building. And then infrastructure. So infrastructure is 20% of total construction output. It's a very diverse sector, and there are large volumes of concrete going into some big bespoke projects. So for example, we've got rail and HS2, energy, a lot of concrete is going into new nucleus. So for example, Hinkley. So we did interview stakeholders for both of these, but they're quite bespoke projects. So we decided to focus on roads and calculate an emissions sink factor based on a standard concrete slip form road barrier, which has an emissions factor of 5.65 kilograms of CO2 per meter cubed of concrete. So this is just an overview of the whole primary use model. A key part is at the end, the activity input is all based on bottom-up data apart from the mortar sales, but we do cross-check it against MPA top-down cement data to check that we've got consistency within the model. We've also compared our primary use prototypes with some examples that are in 16757, and you can see we get similar but slightly lower emission sink factors. I think that's not surprising because we've got slightly lower CEM1 content. So that gives us confidence in our calculations of the emission sink factors. Okay. Moving very quickly onto the end of life and secondary use of concrete. So the literature recommended that we develop a UK specific end of life model. We've looked at demolition timescales, getting some input from the National Federation of Demolition Contractors. There is a limited evidence base for how much of construction and demolition waste is concrete, but we've taken this value of 59% from work done by RAP and BRE. And our activity data comes from DEFRA statistics on waste recovered, and specifically construction and demolition waste recovered. We're assuming that all the end-of-life concrete is coming from commercial buildings, but some of them will be composite frame typology, but historically, concrete frame typology also had about 50% of the commercial building market. So we assume that 50-50 mix, and we assume that nearly all the secondary life concrete goes into groundworks, and that we take into account, we subtract the carbonation that's already occurred during the primary use life, but we do find a considerable amount of carbonation will occur in the secondary life, which is equivalent to over 100 kilograms of CO2 per meter cubed of waste concrete. So I said I'd show you some experimental data that we've got from the University of Dundee. So these are some test cubes which are about 18 years old that are recently tested at the University of Dundee. We also have some BRE test cubes which are not as old. They're 2 years old. What we found from looking at all this data was that for a normal strength, so if we're less than 40 megapascals and we're looking at high CEM1 concrete, then there is good agreement with the parameters given in EN 16757. However, for concretes that are higher strength, so more than 45 megapascals, and or which have a much higher SCM content, there is much less consistency with EN 16757. And this is quite important because these high strength and high SCM content concretes are being used a lot in HS2 and Hinkley and the infrastructure projects. So we've made, alongside the reporting that we're doing to BASE, we've made recommendations for future work. So there are many ways that we could improve the model. For example, a key one would be to disaggregate the infrastructure sector and to improve the evidence base for end of life and secondary use, and eventually develop a more detailed UK Tier 3 model. We've highlighted the experimental carbonation research, that more research is needed to understand that although it's outside the scope of this project, it will be needed to accurately estimate the national carbonation sink. And then also there are wider implications of the work. We're talking with BASE about how we're taking it forward to including the carbonation sink within our UK National Greenhouse Gas Inventory Report. There are other carbon accounting systems within the UK, like carbon budgets. And then also, how can we help other countries to develop similar models working together with the IPCC? And how we can maximize the permanent carbon sink potential of concrete. So do our demolition practices currently optimize the carbonation potential? How can we advance accelerated industrial carbonation technologies? So that is the end of my presentation. So thank you very much for your time, and I look forward to your questions.
Thank you very much, Rachel, for that. So that's fascinating stuff. It's good that carbonation can be good rather than just causing rusting of the reinforcement. So we have got time for some Q&A now. So can I please ask you to come back on camera, if that's okay? And we have got some questions. You were on camera again. Okay. So our first question is to Janet, if you're there, Janet. Yep. So it's from Mandy Truby. The voided beam performance seems too good to be true. Have you theorized why this happens? The former looked like it may have been left in place. Was it a steel former? And if so, is that effectively reinforcing the section? Because this is a very typical application for concrete lintels, and many thousand lintels must be used around the world. Just before you answer that, Jenny, it does look like it's too good to be true. But I know exactly the same was found by Andrew Beebe at Leeds and also by Michael Collins at Toronto. And it is to do with preventing the struts from sort of bulging where you cut out the concrete and weakening. But have you got any comment on that, particularly about the formwork being left in place?
Yes, thank you. Yeah, no, it does seem too good to be true. The formwork wasn't left in place, actually, so there was no steel in that interior void. And how we postulated is these are shear critical beams, and so the critical shear cracks develop in the prismatic beam and, in fact, impinge on the ability of the beam to resist as an arch. Whereas by taking the void out, we've sort of preferentially put the forces through these compressive struts. The concrete's then taking compressive forces in the compressive struts. The steel tie is taking tension in the tie, and that's a very highly efficient way for the beam to carry load.
Excellent. Thank you very much, Janet. So the next question I have is from Ed Newman Sanders. This one's for you, Rachel. Regarding recarbonation of concrete, other than increasing the surface exposure of concrete, is there anything else, such as mix additives, that can be done to enhance this?
Okay, so first I'd say I'm not a chemist, so I think for things like mix additives, that's probably an area for future work, and where my cement chemistry expert colleagues will be able to say more. I think the other thing is that this is essentially an accounting model, and we're very aware that it's, we don't want to present carbonation for the sake of carbonation. We've got to take into the other aspects, avoiding corrosion of reinforcement and correct specification. I think at the moment, the most promising area for increasing recarbonation is carbon curing of concrete, which is in development but needs scaling up to industrial scales. And I think it's also, my understanding is that technically carbon curing is simpler for precast because you've got that factory controlled setting.
Okay, thank you very much, Rachel. That's great. Another one for you, Janet. You talked about mixing different grades of concrete. What do you see as the sort of future sort of practical applications of functionally graded concrete?
Thank you. But I think what's great about thinking about materials more generally is this alignment of performance, material, geometry, and placement is key. And really within that, doing best practice across that is really what we all strive to do. I think what functionally graded concrete allows us to then do is in fact promote even further cement minimization. So really looking at what our requirements through an element would be, and therefore, for example, if we need a durability layer, put the durability layer where we need it. In terms of the practicalities, probably in the first instance, places like precast elements that can be fairly well known as to what the performance requirements are, and horizontally layered, that would be, I think, probably a first application area.
Brilliant. Thanks very much, Janet. And then we have another one for you, Rachel. And I think you touched on this right at the end, but how accurate is this, the model? I mean, is it accurate enough to be used in the UK greenhouse gas inventory, for example?
Okay, so we've tried to make the model as robust as possible, but as I explained, there are 3 different tiers of complexity fitting within the IPCC guidelines, and we've developed the model at tier 2, which is the intermediate level of complexity. So there are many assumptions. We've made it as robust as possible. Within the IPCC framework, having uncertainty in the model does not per se disqualify it from it being included in the greenhouse gas inventory. So some of the sources and sinks that I talked about, specifically in the land use change and forestry sector, they're very high uncertainty estimates of plus or minus 50%. As part of the work we've done with Ricardo, which will be included in the final published report, we have tried to quantify the uncertainty. The other thing is that in terms of the IPCC reporting, high uncertainty, it doesn't disqualify it, but also those areas are actually prioritized. They have to be ranked within the whole national greenhouse gas inventory report, and the areas that are big sources and sinks and have high uncertainty are prioritized for future improvement work.
Okay, that's absolutely great. Well, we don't have any further questions, but we've also reached the end of the session as well. So thanks again for 2 very, very interesting presentations. So we are going to take a quick break now, just for literally 10 minutes. So we are going to be starting promptly again at 20 to 3. So speak to you all again soon. So welcome back, everybody, from that very short break. We're now going to move into session 2, which is going to be looking at bulletins and also some recent projects. So our first speaker in this session is Dr. Christian Glasser. Now, Christian is a Chief Technical Officer and President of Structural Health Monitoring at fibUK. He's a member of FIB Commission 5, and he's been convener of Task Group 5.8 since 2020. So Christian, if you're there, is going to be presenting on Bulletin 97, External Tendons for Bridges. So I can see you're ready, Christian, so over to you. Thank you.
Yeah, thanks, Chris, for introducing, and hopefully everyone can hear me. So in the following, I want to give you an overview of the Bulletin 9017. The Bulletin 9070 is about external tendons for bridges. It was published early 21, and within this presentation, I will not run through the entire bulletin, so don't expect this, so everyone has the chance to read in detail. I will highlight some of the, let's say, most interesting chapters, maybe. So you see here a list of the content, and so really don't expect everything can or will be explained in the next 29 minutes. So generally, I believe everyone is aware about external tendon technology, a technology that we are now using for 50 years, and main applications in new structures, so as well for cast in place bridges, as well for precast segmental bridges. So besides the application in new structures, there are also a lot of repair and strengthening projects, which I will also show you at the end of this presentation. So before we go into some further details, I want to highlight a little bit the components, but also showing you different systems that are state of the art, but also that have been used maybe in the early times of the external post-tensioning technology, with maybe some also lessons learned. Starting generally here with an overall tendon layout of an external tendon. So major difference to a bonded tendon is, of course, that we cannot have continuous deviation. So that means the tendon typically is straight unless we have defined deviation points. We have anchorages similar as with all tendons, and I will go into more details to all the elements that are shown here within the next couple of slides. Starting high level with the different type of tendons that are on the market. So where are in the upper box, you see various types consisting of a PE duct with tensile elements in, either strands or wires, corrosion protection done by a filler. Nowadays, we use here flexible fillers. Originally, when the technology started, the majority of the projects was executed using grout, cementitious grout here. We have also solutions where we have the duct, PE duct still with monostrands in and a filler. I will explain you later on why this filler still is necessary. Function here is not corrosion protection. It's more embedding the strands in deviation areas. We'll come to it later on a little bit more in detail. There are then monostrand solutions without, let's say, fillers. You see different types in round ducts, in rectangular shapes. Monostrands, even with double coatings or double sheathing on. Especially Japan, they have a completely different approach where they use epoxy coated strand without any further sheathing around. And last but not least, on the right bottom one, you see bar tendons that also are used, especially for shear reinforcement for vertical tendons, where you have typically the bar within a PE duct and a filler, or the bar protected by wrapping a special corrosion protection tape around. So that is high level all the systems you see around the globe, and they are explained in the bulletin in more detail. Coming to the anchorages, I would say that is quite similar what you use from bonded tendons. So there are embedded bearing plates or bearing plates that are set on the concrete. There are also multi-plane anchorages. So in the top box, what I've marked in green on the top, that is typically the applications or the type how it's used in new structures. For strengthening projects, of course, you cannot have reinforcement in, you cannot have any trumpets or something like this. So the only thing you can do is having a straight drilling through the existing structure. So, and having then a massive bearing plate on top of it for introducing the post-tensioning loads into the structure. Coming to deviation, that is, of course, a major point of consideration. As I mentioned, we don't have a continuous deviation along the tendon path. We only have it at specific points. And at these specific points where we have the deviation, we have massive transversal loads applying. And to avoid that in these areas, either the pre-stressing steel or the wear of the PE sheaths or of the corrosion protection is suffering, there are specific deviators. So you see different types, either with bent pipes, matrix deviators, as you see in the right bottom, or you have special half-shell deviators that can be adjusted to the deviation as it is in place in the individual project. Yeah, that is even showing that this is tested. So you see such a deviator in a test. So here this test is, or the purpose of this test is to prove that during the entire life cycle in this deviation zone, we have sufficient wear resistance so that the corrosion protection is not suffering over time. So that is a test described in EAD 16. Yeah, some special elements I want to mention finally. So that is for after tendons typically are installed, you place with fixations once tendon length or the free length exceeds a certain length. So here the idea is that these fixations shall avoid too much vibrations in the cables as a result of the traffic. So that are the major elements. So what was originally the idea for using external tendon? Why was 50 years ago a certain need? There are 5 major reasons. So the one is that especially special locations of the tendon had been critical for concreting. So especially here, the connections between the webs and the bottom slabs of bridges. Then topic ease of installation, replaceability, inspectability, and even the chance to add further tendons once traffic conditions change in the future. So that had been a little bit the drivers why this technology was started. Originally, this started in France and in the US. The original type or the first generation of tendons which was used typically used cementitious grout. So that was this type of tendon that I have shown you in the beginning with the PE duct, strands inside, and then the space inside the duct filled with cementitious grout. This was good thinking, but there had been major issues identified. So I call it, this was the first generation where we see after 20, 25 years lifetime, PE ducts cracked, we have voids in the duct, we have problems with corrosion, water in the tendons, tendon corrosion. So simply speaking, there was then takeaway that that cementitious grout is an option, but there are risks in the execution. So only with a proper installation and also quality inspection, this can be considered as durable. As consequences, or just starting maybe with some photos here, what had been observed. So that is a tendon in US. You see other photos that already show failed tendons with corrosion. So here that was quite alerting. That was in the beginning of the current millennium, or in the current century. So what had been consequences? So there had been bans in certain countries for cementitious grout. So France has forbidden it 2001. USA was observing it, and here special incidents had been observed 2010 to 2015. So Florida Department of Transportation was one of the first DOTs also prohibiting cement grout in external tendons. Japan anyhow preferring epoxy coated now, and we see more and more countries that really now go the way to flexible fillers. So that can be a wax, a grease that is used instead of the grout, that allows better or less, that is less critical during installation, allows better inspection, and so on. Also FIB was taking care of this topic. So there had been 2 workshops, 2001, 2004, and as a result, many of you might know FIB Bolitas 33, that is when showing this durability chart, so that there are certain protection levels required depending on the exposure, but also depending on the structural protection layers. And finally, all the external tendons are at least at a protection level 2. So that's also considered in this technology, or is now a new standard, more or less, that is applied around the world. Coming a little bit design aspects, that is also a nice chapter in the bulletin. So what is different to design of standard bonded tendons? So major thing is, of course, we have no strain compatibility at the individual section between the post-tensioning and the surrounding concrete. That has advantages, of course, because we have typically quite small stress ranges. That means fatigue isn't an issue. We have typically we cannot have this continuous deviation. So typically there is a polygonal shape typically applied. We can easily calculate forces, but we have to consider them at all the anchorages and at all the deviation points. And then, of course, we need to have special care how exactly it's installed and so on. So there are some tolerances considered, but overall quite easy. And maybe one disadvantage is, of course, we have less eccentricity compared to internal tendons. That means we have less internal lever arm. That is, of course, a little bit negative, but can be considered for sure in the design. Deviated design I mentioned, and there are various methods. So just showing here strut and tie approaches for calculating forces at the deviator, so that you probably can consider all acting forces in design. What are the major differences in the serviceability and ultimate limit states? For the serviceability limit state, simply speaking, there is no difference. In the ultimate limit states, there is, and the important difference is, as we typically will have lower stresses in the external tendons. So typically in an ultimate limit state, we will not reach the yield stress in the pre-stressing steel. Coming a little bit in the next slides to assembly, and I believe here we have to consider 3 different options. So there are on-site assembled, semi-prefabricated and full prefabricated tendons. Starting with the new structures, as I mentioned, I will also show you a little bit examples on existing structures. For the new structures, we have to differentiate external tendons used for primary post-tensioning and external tendons that are used for secondary post-tensioning. For the primary post-tensioning, the external tendons are installed parallel to the construction process, so we are really within the critical path of the bridge construction. External tendons used as secondary post-tensioning are the majority of the applications in the meanwhile, and typically after all the spans are completed, when for the live loads the external tendons are installed. So as I said, that's the majority, and the other thing is, let's say, technically possible, but has been not proven to be economic in many cases. Coming to some pros and cons of the different type of assembly methods, starting with the on-site assembly, and that is, let's say, the traditional, most flexible and still most frequently used method, allowing really that all the tendons can be separately delivered to the job site. That can be a pro and a con at the same site. As I mentioned, it's on the critical path of the bridge construction. That means any delay in tendon assembly delays the entire construction process, and corrosion protection is applied on site that has dependencies on workmanship, on weather, and so that is something that is to, let's say, has to be supervised, and that has to be carefully executed. Partially or semi-prefabrication is, let's say, resolving some of the problems. So the free length, at least, is applied or can be prefabricated under constant conditions. As the anchorages are not assembled yet, so it's just the free length that is prefabricated, still the length can be adjusted on the site. The anchorages are then assembled on site. That is a pro and con, because still here in this area it is critical to apply the corrosion protection in the right and the proper way. So, and there are also limitations on size and length of tendons due to transport. So here important to highlight again, prefabrication in the free length only, still anchorage assembly at the job site, and critical for corrosion protection is especially the transition between the free length and the anchorage zone. So that is something that needs to be treated with special care. Full prefabrication finally is then the solution that you prefabricate free lengths, including the anchorages. So really here with a tension stiff connection between the PE tube of the free length with the anchorage, with a full corrosion protection applied already in the factory. That means under factory conditions, then shipped to the job site directly prior to installation, installed and stressed, and no further corrosion protection work needs to be applied. What the negative aspect is, of course, there is no length adjustability anymore. So that means before the tendon is produced, the exact length has to be determined. Otherwise, you might have the problem on the job site. What generally has to be done before, when you want to use external tendons, before casting already, here, correct tendon profile is the one what we have to take care before we do the concreting. So really ensuring free passage of the tendons. So that means here special care on the positioning of all the anchorages and deviation parts is quite essential. You see here deviators installed, different solutions. So as I mentioned in the beginning, there are different types of what you see in the picture on the right, for example. That is a solution using half shell elements that can be exactly located in the direction where you have the acting deviation force. Also, if it's recommended to consider temporary intermediate supports along the straight lengths, so that when installing the tendon or the ducts, these are not damaged by pulling them over a rough concrete surface or something like this. Coming to the installation for on-site assembled tendons, so typically you start with installing the duct. Special consideration is taken where you have valves for injection, also considering where you have deviators and so on, when typically the strand is installed one by one. Come to the further works in a minute. Coming to prefabricated tendons, starting with the partially prefabricated ones, so where pulled as prefabricated product into the final position. After that, the anchorage is prepared, so typically the sheathing has to be removed in the transition zone with the right length, so that no bare strands remain in an area that is not corrosion protected. For fully prefabricated, it's quite easy. It's just pulling the fully prefabricated tendon in, secure the anchor heads, and you are almost ready to start the stressing. For stressing, no major differences to bonded tendons, so will not go into detail. Maybe some differences once you use fully prefabricated tendons here. Important is to know that the final length will only achieved after stressing. So typically you need use these stressing spindles to stress them. And then once you have the final load, you anchor them with a ring nut or using some shim blades to do this. For partially prefabricated tendon, major thing is or typically the stressing looks quite similar to bonded tendons, so the anchor head remains fixed, and once you have stressing done, typically the strand protrusions are cut. Now we have a special case, and I mentioned this, these are the tendons using monostrands and having grout in between. So here typically you stress the tendons to an initial force, typically 10 or 20% of the final force to remove the slack of the tendon. And after that, you grout it. Once the grout is hardened, then you stress it to the final force. So the idea is really that in the deviation points, you have not one strand putting transversal force on the neighbor strand. So that is an important thing for the durability of the wear and to guarantee proper corrosion protection during the lifetime. Duct filling is, of course, important for all type of tendons, either done in a plant for prefabricated tendons or on the job site. And very important, of course, is the right position of the valves. So that applies for both. In this slide, you see some examples of a prefabricated tendon. So here in the plant, in this case, a wire bundle is pulled through a wax bath. So, and after that, the entire length of the cable is additionally fully pressure injected with wax. Once using monostrands, you have already the pre-stressing steel protected by the strand producer. Coming to on-site fabrication, here, as I mentioned, you have to consider the concept or the sequence of grouting, taking care that you have inlets and outlets for the air as well as for the grout to allow here really a complete injection. So there are different options described. I will not go in this presentations to the details. Yeah, important is that we make sure that the tendons are completely filled. So there are modern methods for this, you see in the left side. Also, let's say some more robust methods like using a hammer to knock on it are still in place. So that is quite important that we make sure that these tendons are completely filled, and only by this we can guarantee a good corrosion protection on the entire life cycle. Yeah, Final works, corrosion protection, if necessary, assembly of fixations, and smaller things will not go into details. Yeah, as I mentioned, we'll use the last minutes to dive into an application for existing structures. So most of the statements I made applied more for new structures, but also we have aging infrastructure that requires strengthening of existing structures. And I will show it to you on examples. In the bullet you will see several examples. So the one I'm still choosing here is a quite recent project in Italy. It's a bridge close to Ferrara, crossing the River Po. It was strengthened last year, showing you a little bit maybe the project. So it was a bridge with several spans having a double T-beam girder. And what was the problem? So under traffic was a significant deflection. So as you might see in the videos, that is really during trucks crossing the bridge, you see the superstructure with significant deflection. So, and as a result of this, there had been major damages. So there was the idea not to rebuild it, but to strengthen this bridge. And the concept that was planned or designed was using external tendon. So to have an additional bending resistance by deviated external tendons. So you see the drawing on the top and see already some photos how it looked on the job site. So with deviators installed first, connected to the superstructure, and when the tendons, in this case prefabricated tendons, being pulled in and stressed to improve this. So some photos from the installation process. So as I mentioned, there have been external tendons that came on drums, so positioned and then pulled in through the through the already pre-assembled deviators. So different views on the same. Here really impact to traffic was quite limited. So as let's say really everything was prefabricated, so only one lane has been closed, and even for one span, the 8 tendons with 70-meter lengths had been installed in only one day. Yeah, finally showing some photos of the stressing process. So here really in a quite narrow area, it was possible to stress the tendons with lightweight small checks. After that, the project was succeeded. So all the spans had been equipped with the tendons, and the bending or the measurements of the deflection showed at the end that really, the achieved target, or that the target was achieved, and the bridge is now in a really good condition again and can be used for the next couple of years. Yeah, that concludes my presentation here. And as I mentioned, I only went through some selected points, but can really just invite you to read the entire bulletin. That is a very good state-of-the-art report, and want to acknowledge here all the authors and the members of the working group. Thanks to everyone who supported this, and happy to answer your questions later on. Thank you.
Thank you ever so much, Christian. That was great. The timing was also absolutely spot on. From my knowledge of the bulletin, I think it really is a great sort of summation of best practice that's been learned, hard won from lessons learned on projects. And I saw one slide flashed up Medway Bridge, which was one of the things that we designed back in 1999, and it's certainly learned an awful lot about how to do it and how not to do it on that project. So thank you ever so much for that, and we'll take some questions at the end of the other sessions. So on questions, by the way, please do submit your questions now. because we'll have a Q&A session for all of our sort of 3 final presentations together at the end of this session. So with that, we're going to move on to projects now, to hear about some recent projects that have addressed sustainability and low carbon in really practical ways. And our first presentation has 2 speakers. So Robert Jones is an associate structural engineer who's been at Borough Happold for the past 8 years, and he's currently working on Salisbury Square development for the City of London. After that, we have Keith Ellis, who's a principal engineer working for Laing O'Rourke. Joined the business 25 years ago and is currently working design manager for expanded structures at HS2 Old Oak Common. So I think, Robert, you're going to go first. If you could then perhaps just hand straight over to Keith without coming back to me, that would be fantastic. So over to you.
Sure. Thanks, Chris. I'll just share my screen. Okay, that's gone through okay. Yeah, so thanks for the intro, Chris. I'm going to talk to you about the London College of Fashion out in Stratford. I was the lead structural designer on the project, and Keith, the design manager for Expanded, who were doing the structural frame construction. So a little bit about the London College of Fashion. It's this large building in the middle here. It's collecting together 6 locations of the college that are currently spread across London into one dedicated campus building in Stratford. It's part of a series of cultural buildings on the site as part of the Stratford waterfront development, and that's all led by the London Legacy Development Corporation, who were in charge of taking care of the park and making sure the legacy was transformed after the 2012 Olympics. We also worked for the UAL as their kind of partner client, and our direct client was Allies & Morrison Architects, who led the design of this building and the master plan of the whole scheme. So this is a bit more about where it's located. It's across the river from the London Stadium, alongside the same riverfront as the Aquatic Centre, and in the International Quarter just behind it in Stratford. And the other buildings on the site, so we've got the V&A Museum, BBC Music Studios in the south, as well as a dance theatre, as well as a series of residential buildings at the north end of the site that basically pay for the whole thing. So to go through the kind of conceptual design for the project to start, the architects were really inspired by this building in Venice, where you have an inner courtyard and atrium space that's surrounded by a circulation route that then connects together all of the kind of functional spaces that are surrounding the outside of that. They really loved the idea of that for the university, and thought that would work really well for kind of cross-pollination of the different parts of the college. They also took inspiration from the area, so on Carpenter's Road, which is the road that runs along the back of Stratford waterfront site. There were previous factories, workshops, various sort of industrial life in the area that they wanted to kind of emulate and bring forward into the modern design. They also took inspiration from the previous LCF locations. So this one in Lime Grove had this kind of workshop feel to their location, where it was very functional, had a regular grid of columns along the facade, steel frame windows, lots of exposed structure, exposed services. So they really loved that and wanted to bring kind of a modernized version of that into the new building. So building on that Venetian building idea, they kind of came up with this split for the building of the inner heart of the building, which is fixed. It's a monolithic kind of heart of the building. It's purpose built for circulation, cross-pollination of all of different disciplines within the college, and sort of informal breakout spaces that happen there. So I'll just move back on there. And then surrounding that is more of the workshop spaces and deliberate spaces that are for things like the timber timber working, you have leather working, you have a sewing room, all of these different spaces that are kind of within the college that are deliberately serviced by their spaces around the outside. And they really like the idea of this kind of kit of parts that is kind of assembled together on site. It's pieced together onto the side of the main heart space. And so it's deliberate and specific, and it's for the teaching spaces then. So overlaying that with the structural scheme, you then end up with this kind of inner heart square within the building, which separates the inside and the outside of the heart. A perimeter of columns regularly spaced around the outside, and between those two vertical structures, you can span a one-way structure from in to out, and create this fully column-free space that wraps all the way around the perimeter of the building. Then on the inside of the building, you have a regular column grid of closely spaced columns that allows the architects to kind of play around with cutting holes in the slab, varying the atrium as it goes up through the building, and also for vertical circulation, both in terms of people flow, but also emergency egress stairs, lifts, service risers, and the like. So this is kind of the idea, and putting the main kind of stability structure into that heart wall gave them the flexibility within. So just having a look at that in 3D, you then have kind of this, as you can see, the heart that comes up through the space is this monolith through the middle of it. You have a public podium which wraps around the outside of the building with a colonnade that supports the structure above and transfers out that structure down to the lower levels. And then the bolt-on pieces around the outside of the workshop spaces that are prefabricated and assembled on site, attached to the building, and they step in and out to give the mass of the building. The architects played around with geometries for the heart wall, so there's they had a look at sort of a trapezium arrangement, which is from a previous scheme of the building. They looked at a kind of Toyo Ito arching concrete feel to it to make it feel like it's kind of carved out of this one monolith of material. But we ended up with a much more regular kind of column and beam arrangement, which was really in itself really well suited to a prefabricated approach where a lot of element sizes were repeatable, and there could be a real kind of efficiency in the prefabrication of that. There was a real push for prefabrication on the building, mostly driven by program. The school had to be open for originally it was September 22. Which was pushed out by a year because of COVID, but there was a real push to get the building finished in that time. So it drove the whole critical path of the entire Stratford waterfront master plan. So there's a real drive to get as much prefabrication into the building as possible to meet that deadline. The architectural scheme below level 4, the transfer level, there was a lot of difference floor to floor. There was a lot of kind of organic shapes and in situ concrete needed to meet the architectural intent. And so it kind of made sense to keep as much in situ concrete in those floors. And then you've got above level 4, all the repetition, regular floor to floor heights, similar kind of floor layouts. And that really suited a lot of precast above that point. So we had precast edge beams, precast columns, hollow core slabs spanning the one way from the inside to the out, and steel structure on top that was obviously prefabricated. So you can kind of see that in the plan there. That was the idea originally, is to have that kind of monolith of carved out in situ concrete in the middle, and the bolt-on precast around the outside. What we ended up with as well when we went into stage 5, working with Keith and their team, was they brought in even more precast. So they brought in twin wall in the cores over here. They also brought in precast lattice planks for the heart slabs above level 5 and above, as a kind of permanent formwork for the flat slabs in there. And so really 2/3 of the building is prefabricated with a little bit of in situ stitching to the top surface of those slabs. So we had a hollow core, precast columns, precast beams. I'll talk about a precast transfer slab that we got together in a few slides time. We've got all the steelwork and then a series of stairs and precast landings throughout the building. So it's a really kind of kit of parts approach to the building. In the design stage, prior to Expanded coming on board, we were working with Mace as kind of constructability advisors and looking through the sequencing of the project and how this might work. So the intention was that the heart would be built first, might be 2 or 3 floors ahead, and then the workshop spaces around the outside would follow on afterwards. So we had to think through if the heart space is going up first and the precast columns are going in there, how do we then attach the hollow core slabs into the side of that and make sure that we get the right connections into that. So looking at all the different interfaces through with column, in situ beam, maybe a precast, a concrete core ball or a shelf angle, then a tying in slab, column above, and then bringing a hollow core through. So looking at all of the detailings before we actually got a contractor on board, trying to kind of safeguard it and explain our assumptions in some fairly, well, hopefully robust detailing, and looking at, once your in situ is in and your shelf angle's on there, can you drop the hollow core on there, have some bars ready to extend out for robustness and diaphragm, and then tie that all in together. So that was a key interface. And also a lot of this is exposed visual architectural structure, so it needed to look good at the same time. So this is during construction, there's a bit of tidying up to do, but that interface ended up really clean. And I think all the thinking that we went through, both in the design stage and with Keith and his team, really paid off on those. Another interface is at the facade edge, and the architects wanted to make sure that this kind of feature part of the building where it's looking out over the park really was a clean interface. So looking at the precast edge beams, the precast columns, how it all threaded together, how the hollow core worked on top of it, pouring the slab over the top and then fixing the facade onto it. They really wanted to get to grips with how that all worked. So we worked really well with them through the design stage on that. And looking at staging in terms of details and making sure that we could get the tie-in of robustness and diaphragms there. One of the key interfaces at the edge was making sure that we could get the column bars up through the precast beam and past the edge of the hollow core, as well as making sure that the hollow core could bear onto the interface there. And we ended up looking at a detail where you notch out the end of the hollow core, and yeah, all the will in the world. We thought this was the right way to go, and then during construction, realized that the hollow core needed to be a straight edge there to get the sufficient bearing onto the surface and a continuous surface through there. And so once Keith and his team were on board, they were able to justify pushing the column rebar back to allow that interface through to happen. But that could only really occur once they were on board and we could work through those interfaces. But that's an idea of what it looks like on site. Some couplers there and some in situ tying on the top there, tied to the hollow core. You can see how that all is all fitting together with the bars pushed back into the beam. And then what the architects modeled in the design stage and how it ended up looking, which is nice and neat and clean as an interface. And just a comparison to the inspiration image there, you can see that there's a lot that's come through in the new design, and it's modernized, but it still has that same kind of feel to it, which is what they're after. I mentioned the transfer slab up at level 10. So we have a set of columns that step in by 3 meters above level 10, and there's 4 more stories above that. These are 13.5 meter spanning transfer beams that we had to work through with the architect. We ended up settling on 1 beam per column to minimize the depth of the whole floor plate. And I believe I saw Andy Truby posting a question on the chat. We worked with Andy Truby to look at the feasibility of doing a post-tensioned scheme for this. And in order to get the weight of these elements down, all of this had to be precast to stay with the kind of visual and approach of the building. In order to get the weights of the precast beams down to the tower crane limit that we had set from Mace, which was 10 ton. What we ended up doing is doing this sort of shell beam, similar to kind of the bridge construction that Christian was talking about, having a shell beam there with the an in situ stitch portion in the middle of that with tendons running through there, and kind of precast block on the end to get the interface with all of the connecting elements, the edge beams and the columns coming up and down through that interface. So had to think through all of these interfaces during the design stage, and I think Keith has got some slides to talk through how that actually eventuated in the detailing it out on site. But just an image of what it looks like on site, and it's nice and clean and looks like a great finished product, albeit there's a lot of complexity in the inside of that. Just talking about precast columns, because that was one of the key sort of challenges as we went from design stage into construction stage. You can see how many precast columns we had, so it was quite a sort of heavy processing task to communicate the design through to expanded. But most of the columns are, as I say, around the perimeter and around the heart wall. Most of the columns are defined by, I think 90% of the columns are defined by 3 shapes. So that was really well suited to a precast approach. One in the design stage, we had a precedent project where the way that they connected the columns together on site was that they had full height grout tubes, which they would thread the rebar through. You could use couplers, or you could lap the bars if there was room in that space to have the bars sticking out. And then once they were in place and propped, then you would grout them up, and that would fix the bars in. This was the alternative to having partial height grout tubes for just the starter bars, which would then have grout holes off the side of the columns, which would be visible, and the architects didn't want to see that. When we went to the construction stage, Expanded wanted to do column shoes, and the key benefit of that is that once you bolt these up on site, they're fixed in place, and they don't need temporary propping, and they don't need the grout to set before they can continue on with the next stages. So there was some real benefits to program, certainly, and health and safety for these on site. The only thing we had to deal with is that because they're a proprietary product, they take up a certain amount of room, and we had to lay out those within the column section. So you could only fit so many in there, and we had to work that through with Expanded to see how much you could actually fit in to meet the original design loads that we had on there. And in some cases that they weren't sufficient for the original design loads. So we went through a process to revisit the original design and kind of iterate back through what the expected capacity of the cross section is. So we actually mapped out how many anchors you could fit in the cross section and what capacity you would get out of that cross section as a result. We put that back into our analysis model and used a program called AdSec to look at the cracked section under a certain amount of loading. So you can get this chart here where with an increase of axial load, you can see how much the section is going to be expected to crack under a certain amount of bending moment. So kind of going through a few iterations, you can settle on kind of a coincident moment with a certain amount of stiffness reduction from full section. So you can apply that back into the analysis, and then once you are applying a stiffness to that connection that corresponds with the moment, then you kind of settled on a solution. And then looking at the capacity of the section off the back of that, we can get this graph again in ADSEC, which is a biaxial bending capacity graph where you get a bit of extra bending out of the biaxial loading. And as the axial load goes up, the graph moves out. And you can then plot all of your column connection load points onto the same graph. A little bit hard to read what's actually working and not working in this. But if you then plot your axial load on the Z axis, you get this kind of biaxial capacity vase where the red surface is the capacity outline and all of the green points are the load points in kind of XYZ of biaxial bending and axial load. You can see if they're all fitting within that vase, then the columns should be working. So we were able to kind of communicate back that through to Expanded and say, once you do your final design, we think this is a workable solution. But that was quite a bit of work back and forward between ourselves and Expanded to get those to work. That's my last slide. I'll hand over to Keith now, who's going to talk about the construction stage.
Thanks very much, Rob. That's great. Yeah, so just moving on then. It was, as Rob said, it was pretty much a building of two halves. Below ground floor, we had these very aesthetic organic shapes, and above level 4, it became very geometric. At the RIB stage 4, predominantly it was an in situ design. There was elements of precast in there, but obviously Expanded were employed to bring efficiencies to the construction process by deploying modern methods of construction. So, you know, as Rob said, we like working with kits of parts. We manufacture them off-site in the factory conditions. We can deliver them to site, bolt them together fairly quickly, and with a reduced workforce. And as Rob also mentioned, just as we was getting going, we start design back end of 2019, with construction starting sort of in spring 2020. COVID hit, and so we got shut down by the Mayor of London, and we had to quickly bring together risk assessments to allow us to get back to work. And a lot of that risk assessment was about keeping the workforce apart, and precast clearly helped us in this endeavour. I think it helped us keep going as fast as we did. So there was certain elements. There was a fundamental change in architectural aesthetic in certain elements. So the inside of the heart was originally sort of an in situ slab with a monolithic construction. We was looking at introducing a kit of parts with, you know, elementized with joints between them. So we did an awful lot of work with Bureau Happold and Alloys and Morrison to sort of agree where these joints were, and there was an awful lot of coordination done with sort of slabs, walls, and beams, all the components, to be honest. After a bit of work, we agreed we're pretty much going to keep the level 0 to 4 as in situ. I'm talking in broad terms. There's always exceptions, but level in the heart slabs, level 5 to the roof were lattice planks, stability cores. Level 0 to roof, we converted all to twin wall, and the level 4 columns from level 4 above were precast, and all perimeter beams above level 5 also precast. So we employed Bryden Wood to do our conversion design, and along with their design, so they took the loads from Bureau Happold, and they took them loads, produced the design, and along with that, they also produced an elementized model. So there's in orange here, these are the precast components. So on the top image, we've got lattice slabs and columns. The green elements are the in situ infills, and we got the cores there. There was a lot of work done. So we took this model and we presented to the design team, and we spent a lot of work getting these joints agreed. It's not just simply putting them where the architect wants, but there's obviously manufacturing constraints on where the joint could go, maximum size of unit to be transported, or the bed size in the factory. So the basis of all our work was these models, really, the in situ model plus all the precast. Along with the precast model produced by Bryden Wood was a lot of metadata, which gave the intent to the precast facility, which SEMC, Centre of Excellence for Modern Construction, which is the expanded in-house manufacturing facility. So they took the Bryden Wood design and completed the rebar detailing, all fully in 3D. The reason for doing the 3D, it was, structurally, it was a very technical building. The loads were fairly high in places, and we needed to make sure we coordinated all the inserts. So we've got the column well voids to get the column anchors through. We've got casted inserts to take our safety screens as we built the job. There's on the columns, all the facade had to be hung, so we had facade anchors and glazing anchors as well. And inside the cores, there's similar coordination with the stairs and interfaces between twin wall and the landings. So there's an awful lot of interfacing to be done. So this was generally built around what we call our digital build model. So you can see the light green here is all the in situ concrete. So we build this from the drawings. If we can't build it in the model from the drawings, then we won't be able to build it on site. So we bring the RFI process a lot sooner. So as we're building this digitally, we're raising the RFIs, raising any queries, we'll get them resolved. So when we are building on site, we've got the model built and we know we can build it out on site. So what is a digital build model? It basically includes all in situ concrete, including reinforcement, all the precast elements, structural steelwork, delta beams, temporary works, architectural metalwork, basically anything we're bringing to site, and we model. You can see in the top here we've got there was some along the waterfront, there was some composite concrete beams with some heavy steel work in. So we've got all the steelwork modelled inside the concrete, including temporary works, etc. And we also brought in the subcontractors, the other subcontractors on the project, so the cladding and MEP, so we can make sure we're getting any castings and voids set in the right place. And we use this, it's not just for visual effects, we obviously use it a lot for coordination. We also, because all the reinforcement was modelled, we call off the reinforcement through the model. We've got plugins for Navisworks, which allows us to generate bar bending schedules. We call them straight off the model. Gives us very good records of what we've actually ordered and what we need to order. The model was also used for setting out, so the engineers had imported the models into their setting out instruments, and they could set out directly visually from the model. They're not having to take dimensions off drawings. And still fixes as well, fixed from the model. So it took a while, give them a couple of months with the tablet, they're all a bit pessimistic, but after a couple of months, you couldn't get the tablets off them. They loved it, especially, in particular areas the steel was very complex. They loved being able to move around in the model and see what was going on. So I'm just conscious of time, but I just want to go through, this is the level 10 transfer beams Rob was talking about earlier, and I just want to go through a little coordination exercise. There was many coordination exercises, but we'll look at these cart columns at the back here. So these are the columns we'd introduced the Pico shoes, the anchors, so that the anchors are cast into the columns below. They come through and the columns above drop on top and bolt on. So at level 10, there's this great big void through here. So that was made up with these precast shell beams. So you drop them in, then you put the anchors in with the stressing heads beneath the columns. Then we've got our in situ geometry, which we've modelled, and we model that to gives our reinforcement detailers the form that they need to, that their constraints basically on when they're detailing in situ reinforcement. So they model their in situ reinforcement that goes in through there. Then we have their lattice slabs on top, which will just span in between the shell beams, avoiding props. The slab reinforcement goes in, and then what was a massive space in between the level 9 and 10 columns, clearly becomes really quite compact, and I think this just shows quite clearly that the importance of having done this exercise in the 3D environment enabled us to coordinate well ahead of time before anything was manufactured or delivered to site. We knew when these components come to site that they'd fit, and they did. The building went together remarkably well, and it was an awful lot of hard work with myself and Rob and the team coordinating all this, and there was some pretty tough conversations sometimes, but it all paid off, and we ended up with a solution we could build, and it went together very quickly. Just really quick, last slide. So I just wanted to do a comparison between what we had on the right here. So these are these level 10 columns with the 8 column shoes prior to Robin's team doing that exercise and reviewing the loads that the columns were taking. Our first revision, PO1, included 4 shoes in the corners. So that enabled us to put the columns up with propless and quickly. But in addition to that, we needed 10 dowels through well voids, and this is what drove that reanalysis really, is trying to get these additional 10 well voids through. That image we saw just now was it was pretty much impossible. So looking back, there was a huge amount of challenge on the project, and I think our cooperation and collaboration, it really shows. I've just got a few images here. So these are the stair stringers. So there was an awful lot of prefabrication. It just flew together. Double height columns, propless on the shoes. These are the heart columns. The cores, awful lot of geometry required around the cores to pick up in situ beams. All this was sort of done well in advance before anything was manufactured. I think in terms of sustainability, I think the amount of there was quite a lot of waste reduction by employing this method. We only ordered what we needed. We knew it was correct when it came in. It was just flew together. And some the architectural elements down on the first few levels they're amazing. It's a lovely project. Really proud to be part of it. So, sorry, that's me done a few minutes late there. But hopefully that was useful.
Brilliant. No, well, thanks very much, both Rob and Keith, for that. It's some really sort of challenging, tricky details there to overcome with your sort of kit apart. It sounds like a fantastic effort to have solved all those issues along the way. So, massive well done. We'll come back to you with questions after the next session. So we're going to move on. Again, on the topic of questions, if you do have any, please do put them in the chat box now, because we'll be picking up with them soon. So we're going to move on to our final speaker. And that is Mike Needham. So Mike's responsible for the delivery of major international bridge and tunnel projects in Ramboll's Major Crossings division. And Mike is going to be presenting to us on the new Storströms Bridge. So over to you, Mike.
Right, good afternoon, everybody. I'll I'll try and keep it interesting for you since it's the last session of the conference. So the new Storström Bridge in Denmark. I'm going to give you an overview of the bridge, explain a bit about how the design was developed, then talk about each of the structural elements that make up the bridge, a little bit about the analysis, and then tell you about some of the lessons we've learned and how it's all going on site. So the existing Storström Bridge is a single rail track between Masneda and Falster in Denmark. It carries road as well, but it's in poor condition and it doesn't have the capacity to carry the increased railway freight traffic that's going to come when the Fehmarn Belt connection is fully open. It would be the only section with a single rail track between Stockholm and Germany once the Fehmarn Tunnel is open. So clearly in need of replacement at this stage. The new bridge is going to be the third largest bridge in Denmark. It's 4 kilometres long, combined high-speed rail and road bridge, and an important part of the Trans-European network infrastructure. It'll be one of very few bridges in the world that carry a 2-track high-speed railway as well as a 2-lane road and a combined footway and cycle path all on one single cross-section. There'll be 44 viaduct spans, 2 navigational spans, and the main bridge will be a cable stay structure with a 121-metre tall pylon. So this shows you a plan and elevation view of the bridge. As you can see, there's a curved alignment stretching over the sea channel. There are 3 main viaduct sections separated by expansion joints. So you have an approach viaduct on the north, then an expansion joint, main cable stayed bridge section in the middle, another expansion joint, approach viaduct on the south. There are 44 standard piers and a central pylon here with 2 abutments each end. The central cable stayed bridge has spans of 160 metres and crosses the navigation channels, while the approach viaducts are typically 80-metre span. In terms of articulation, there are 3 fixed piers to share the horizontal loads on each of the approach viaducts, whereas on the cable stayed bridge it's the pylon that does the bulk of the work there. And there are shock transmission units at the expansion joints so that longitudinal loads, for example, from railway, braking or traction can be carried across the whole of the structure. Also, because of the span configurations and the loading, tie downs are required at 4 locations, so at each expansion joint and at the ends of each of the cable stayed spans. So the different elements that make up the bridge, we have the piers, which typically are cellular precast caissons, and then a multifaceted pier, which varies from 18 to 36 metres high and has a hollow core. We have a 121 metre high concrete pylon in the middle, again multifaceted, lower stem, steel anchor boxes. This forms part of the cable stayed bridge where you have the 2 160 metre spans. There's a 22 metre in situ deck just at the pylon, and then 62 metre precast deck segments are brought in and stitched together to make the deck. The deck itself is an asymmetric concrete box girder with internally bonded PT, made up of 73 metre long precast segments that are stitched together into 80 metre spans. So moving on to look at how the design developed. So the tender process for the bridge began in September 2014, and the Danish Road Directorate, DRD, decided to carry out a competitive dialogue process as part of the DNV tender process. That was actually a year-long process during which the tenders submitted their bids and discussed with DRD and resubmitted bids, and that process ended on the 19th of July 2017. And then in February 2018, a design and build contract was signed with SBJV, which is a joint venture between Itinera, Grandi Lavori Fincosit and Condotti, all of Italy. They also had an Italian designer, Di Miranda Associati, and that team carried out the basic design for the bridge. Once the basic design was approved and it moved into the detailed design stage, it was at this point that Ramboll was brought in. So Di Miranda were retained to do the early piers that are at each end in the abutments, and also some early girders right at the end. SGI, who are already on board as detailed designer for the foundations, for the pylons and the adjacent piers that we call 1N, 1C, 1S. And all of the rest of the piers, the girders, the cable stayed bridge itself were taken by Ramboll at detailed design stage. So looking in a bit more detail at the piers, the whole approach is a modular pier. So these are precast segments separated by joints. The joints are 800 millimeters high. So each of these separate elements is 3.2 meters high, except the pier head, which is 5.3. The geometry, as you can see, varies quite radically from rectangular at the top, then it becomes octagonal, and then it's hexagonal, and then right at the bottom it becomes prismatic again, and is more or less rectangular at the bottom. The geometry is carefully set up so it's identical for the standard piers. So every time you see a C1 or a C2 or a C3 segment, those are all geometrically identical, and you can build your height up through combinations of those. The expansion and tie down piers are similar but different because of the need for a bigger pier head to accommodate the extra bearings and tie downs. Within those precast segments, the reinforcement layout is optimized using a standard template. So there are standard positions for where reinforcement can be placed. And within that, some or all of those slots are used for each pier, but each segment is optimized. The lower pier is precast with its caisson in factory conditions, and the height you can get to is governed by a maximum catamaran lift of 2,200 tons and maximum height under the catamaran of 19 meters. So typically the area you can see in white, for example, on the top left, is all prepared in factory conditions. The precast pier head is cast on shore and is eventually post-tensioned, and it's lifted out with the upper pier stem. So again, compared with the top left, all of the items that are red are also a second large cast that is lifted out later, and then the two are stitched together. A little closer look at the pier joints. So the pier joints are 800 millimeters high between precast segments. There are embedded steel sections, which you might be able to see in light blue on the right-hand side. There's 4 of those that are used for temporary support and handling. So you can see in the photo it's being lifted using those steel sections. There are shim plates put in between those 2 sets of H's when they come together, which are used to control tolerances, primarily tilt. The perimeter bars are straight and they're lapped in the conventional way, but where more capacity is needed, additional headed bars are added, and they're added in the interior of the section, and they are staggered, which is what the diagram at the bottom is trying to show. And because of the stress patterns that develop around headed bars, reinforcement links are needed to confine the concrete in those areas. So moving on to the pier head. The pier head is multifaceted, so it transitions from a rectangle at the top to a hexagon 5.3 meters down. And it also has an access void through the middle of it. The access void is increased in size at the pier head to allow space for a recessed inspection platform so that bearings and shear keys can be inspected safely from the middle. And because of this central void, you end up with quite significant tensile stresses along the walls. And it was therefore necessary to pre-stress the pier head in the transverse direction that's perpendicular to the bridge span. However, the architect didn't really want to see lots of visible pockets for pre-stress. So we spent some time with them developing a solution where we fix 8 pre-stressing tendons in each pier head, but only 4 of them are visible at the end because there's dead end anchorages used internally in the pier. And then the 2 pockets were combined into one larger pocket that would be nice and clean when it was grouted up. Looking at the pylon consists of a reinforced concrete caisson at the bottom, then a lower pylon section that tapers in plan and varies in cross section from trapezoidal to hexagonal and then back again. All that has a void through the middle of it for inspection and maintenance. Then the pylon power joint, which is the piece that connects the deck and the pylon together. That's post-tensioned longitudinally and vertically with two separate systems of tendons. And the upper pylon projects above that, and that has three distinct sections. There's a base zone, then an anchorage zone, and then a tip zone. Because the bridge deck is curved in plan and because of the eccentric railway loading, you get significant moments on the pylon, and this leads to the need for vertical pre-stress running through the pylon on the west wall. The foundation itself was designed by SGI, but it was reviewed and adopted by Ramboll. It's a cellular construction to enable the foundation to be floated into place, and it includes the first stage casting of the outer shell of the lower pylon. So you can see in the middle the lower pylon shape emerging. There are also temporary vertical tubes and box towers which were added so that it would float during installation and then could be sunk onto the seabed when required. The lower pylon is an interesting tapered shape. It needs a second stage casting below water level. It was designed primarily from a global model, but second order effects were evaluated and found to be less than 10%, so not particularly significant. What was significant, however, was the global ship impact, which is up to 65 meganewtons, and that required a shell model to look at the local ship impact and also some quite advanced dynamic analysis, which we'll talk briefly about later. So moving on to the power joint. So this is the monolithic connection between the deck and the pylon, which is shaded in red on the right-hand side. There are two distinct zones to this. There's the haunch zone, which is underneath the deck, and then the diaphragm section, which fills the whole of the deck section apart from this access way here. So for this, we used a 3D solid model to determine stress trajectories for strut and tie verification. We also used a local shell model for the transverse deck design. The upper pylon extends some 70 meters above the deck and tapers over its full height. For this, we needed to verify it in the global model, but we also needed to consider second order effects. So semi-global models and local models were used to verify that we were picking up all of the effects we needed associated with the global model. You see some typical mode shapes here, showing the extent of deformation in different load conditions. The anchor boxes formed from 10 discrete steel stay anchor boxes. Grade 460 was needed because of the various site constraints, notably that we could only lift 16 tons per anchor box because of the size of the tower cranes that were available. It was designed so that the skin plates can act as permanent formwork, and it can then transfer the forces into the concrete using shear studs that are on the back as you look at this diagram. A key feature, of course, is the stay cable damping, and that's actually provided at deck level in this case because the guide pipes in the pylon are just too flexible to provide a rigid damper support. So moving on to the stay system. The stay system has a single line of cables centered in the deck, with 18 number parallel strand cables per span, and up to 103 strands per cable, with some spare contingency at the anchorages. Deck anchorages at 7 meter centers, pylon anchorages at 1.5 meter centers. And as I said, the stay damping system is fitted in the deck anchorage guide pipe. There's a two-stage stressing process. So because of the construction sequence, the first stage is you have this in situ portion of deck. You then lift in your precast deck segments each side and stitch those to the sides on temporary towers. And at that stage, the first 9 pairs of stays can be stressed. Then the second stage deck comes in and is all stitched together. And at this point, the remaining stays can be stressed. And then the temporary towers can be removed. The deck is pretty much unique, really. It's driven by both geometrical and safety requirements, and arises from the trying to fit a combined road and rail on one single cross section. So you have this slightly unusual, to say the least, top slab, which steps down and then comes across. You have your railway this side, your road this side, and then on the right hand side, as we look at it, a footway. So the railway on the left, this cross section actually allows for a derailment upstand and an emergency platform. And the emergency platform is designed so that it's at carriageway level, which means there's easy, safe access to the carriageway in the case of incidents on the railway line. Having got that cross section, then a key feature is the spine beam, which is shaded in blue at the top middle. This is obtained from the overlap of the railside and roadside top slabs, and this provides an intermediate stiff vertical support for the top slab that would otherwise have to span almost 14 meters between the two webs. The spine beam is in turn supported by delta frames, as shown here, angled, that's then stiffen the thin-walled girder cross-section against distortion, which is a big issue due to the highly eccentric rail traffic loading. The delta frames are typically 0.38 by 0.38 meters square cross sections, and they're pre-stressed with 4 strands of PT. And of course, the pier diaphragms also provided rigid restraint against distortion. So the typical deck on the approach span is 80 meters overall, which consists of a 73-meter fully precast segment, which is designed so it fits precisely on the 4,000-ton lifting limit that we have due to the cranes involved. Then there's a 1.1 meter front stitch, which is on the right of this diagram as you look at it. On top of the pier head, there's a 4.8 meter partially precast, what we call segment 0, which contains the diaphragm. That's restricted by a 250-ton lifting limit, and so there isn't room to put the cantilevers on it when it's lifted in. So the rear stitch, when that happens, has to deal not only with stitching the girders together, but also has to include the cantilever sections. The post-tensioning for those beams is internally bonded post-tensioning, typically 22-strand tendons. The bottom slab and web pre-stress, shown in blue here, are done in the precast yard before it's taken offshore. And then once it's offshore and in position and the stitches are being made, we can stress the red tendons, which give continuity of the deck. So a little look at the construction sequence. So the sequence is designed around simple lifting equipment using a hoisting tower, lifting arms and hydraulic strand jacks. So the units are brought in on a barge. They have the lifting arms, which are sort of in this pinky color, attached already. Those are retractable, so they can slide the deck across, and then these arms come out either side of the pier. They can then be connected to strand jacks on the yellow hoisting tower and lifted up into position, ready to be stitched together. So a brief discussion of the analysis and the way that was carried out. For this, we decided quite early to use a single global model for the full 4-kilometer length, but divided it into the 3 frames that we discussed earlier. So the north approach, the south approach, and the cable stayed could all be isolated as separate global models if required. The longitudinal flexural design was all done within this global model. That includes modeling things like creep, shrinkage, pre-stress, the construction sequence. So it was a very big model. It took a very long time to run, and it had a lot of load cases and foundation conditions built into it. In order to make it more manageable, submodels were extracted for the pier design. The whole global and local model arrangement was set up using parametric geometry, which is pretty much essential given the amount that the geometry changes, but it did fit very well with being described in parametric terms. And similarly for the reinforcement layout, because we had standard reinforcement template positions, we were able to parameterize that design as well. So this enabled us to develop really quite highly automated structural design processes that enabled us to look at every single segment of every single pier and every single girder separately, and to determine what the optimum concrete and reinforcement layout would be. It also included non-linear modelling for P-delta effects, which again were done on local submodels that were extracted from this global model. And we even went as far as to put in automated calculation reporting, so the calculation reports that were generated for submission to the checker took their values directly from the model. Ship impact, as I said before, with up to 65 meganewton ship impact in places became very important. We had to do a dynamic simulation in order to manage these high ship impact loads. We had to look at multiple load scenarios with impacts from all directions, including deckhouse collision with the deck as well. These models included non-linearity of geometry, materials, and foundation stiffness. So a lot of setup, a lot of iteration, a lot of validation that we were getting the right answers. And they were supplemented by local finite element analysis for the reinforcement in the actual impact zone itself. So having said all that, what did we learn from the process? I think there are a number of items of good practice that we'll certainly be taking forward into our future designs. So the whole idea of the large scale onshore assembly worked very well, had a really good factory setup. There was a lot of repeatability in the way the elements were done, so they were quite standardized, and that suited a precasting yard very well. The use of the standardized geometry and the standardized reinforcement templates made it very easy to communicate what was required for each of the different segments, and also gave us a framework for working with the parametric design. The parametric design itself and the reporting went very well. It enabled us to reanalyze very quickly if there were changes, or to look at slight differences in load conditions or foundation conditions, and also to reassess things if anything changed during construction. We learned a few lessons as well. The stitch joints we minimized as far as possible, but they were very congested, and even when we'd taken out all the reinforcement we could manage and simplified the detailing, it was still very difficult to get good quality concrete in there, especially at sea. Hence the decision to use quite large precast onshore units, stitch them together onshore and then take them out. The complex geometry was really tricky, especially for reinforcement detailing, but also for just things like looking at some of the analysis that was involved. Some of our strut and tie models were quite interesting, and there were a lot of issues with making sure everything fitted properly and could be built. The asymmetric cross-section was a big challenge, especially combined with the curvature, and the deck team particularly spent a lot of time looking at how to deal with that, and similarly the pylon team with the need for the pre-stress on one side only. And finally, the complexity of the single global model. Modeling 4 kilometers of a bridge this complicated meant very long run times, and we spent a lot of time with our software supplier and our IT people working out how we could get the runtime down, which actually we were able to do, having investigated more closely. They gave us some good ideas, and we ended up being able to run using virtual machines in the cloud, which at least took the load off the desktop computers. And so to finish with a little bit on the site progress. So here you see the factory. This is building number 2, which makes the precast girders for the deck. So you'll see that everything gets slid out through that blue curtain, and you've got a few units in storage here outside. You see the yellow lifting arms that are attached, ready to go, and the red is one of the cranes that helps to move things around the site. This is what a typical lower pier stem and foundation looks like. So that's something like 25 meters across. You see it's on self-propelled modular transporters to get it out to the barge. When it gets there, it sits on the barge. There is a big catamaran crane here, and then it's taken out to sea. the barge is removed when it's hanging on the catamaran and it's lowered down onto a pre-prepared gravel bed. This is a pier segment up close. So on the right, you see it in the factory, and that blue is the steel shutters. And this, you can just about see in the holes on the left and right the reinforcement poking through, because that's where the steel template is that sets the position of all those bars. On the left, you see the finished article moved out of the fabrication yard, and you can see perimeter bars. You also see at the top the headed bars, and then there's a crane ready to move it. And this is what it looks like when it's out at sea. So here we have a pier that's fully assembled. You can see the distinctive pier head shape, with access up to the top to finish off the works up at the top. And you start to get a scale on the right hand side of just how big 4 kilometers of bridge looks like. So you've got 5 or 6 piers you can see there spread out. Currently we've produced and installed the first 5 pier heads. 38 pier segments are produced but not necessarily in place yet. 10 pier segments are placed offshore, and we've cast 8 of the offshore stitches joining the lower pier to the upper stem. The pylon was a big event. You might have seen that on LinkedIn if you follow the bridge at all. So this is it in the yard and then being floated out. You'll see the ballast boxes and pipes that give it the flotation capacity, so that when the barge is removed, it can be sunk in a controlled manner. And this is what it looks like inside the second stage casting, looking down from on top as they do the in situ work within the shell. And here a view of the deck. So 7 girder segments are complete so far. For the first segment, 0, that's been cast offshore now, and that's one of the big milestones on the job. The next segment, 0, is nearly ready to go offshore, and we started pre-installing some girder stitch reinforcement as well. So lots going on, lots to do still. There's still a couple of years, sorry, 3 years of construction to do before we're ready to open, but it is starting to take shape, and it's quite impressive when you see it on site. Thank you. That's the end of my presentation, so I'll pass back to Chris for some Q&A.
Brilliant. Thank you ever so much, Mike. Again, sort of similar to the previous presentation, hugely complex geometry issues, particularly to overcome. So thanks to all the speakers. If we all come back on camera, if that's possible, we can get Christian, Keith, Rob and Michael to come back on, and we'll take some questions. We've probably got, you've all done very well to stay on time, so we've probably got time for a couple of questions each, but let's see how we get on. So the first one I have is for Christian. So this is from Akram Malik. So generally we use external tendons up to 150 to 200 meters long, and this is one of the advantages of using external tendons. What are the limitations on length and type of tendon when external tendons are fully prefabricated?
Yeah, thanks for the question. I would say in principle, the limitations are coming from the production plant you have. So typically you produce in a straight length. So that is the limitation on length, because you don't have any limitations on the injection itself, because everything is controlled. So that is not limiting it. On the size, of course, you have limitations on the duct diameter, because the larger the duct, of course, that limits the bending radius. So just making one example from the largest prefabricated tendon we did so far, that was a roughly 300-meter long cable with, well, we are using wires, so 84 wires, that is roughly a pre-stressing force of close to 4 meganewton. So these 4 meganewton tendon, 300 meter was, let's say, the extreme one what we produced and installed so far as prefabricated version.
Brilliant. Thank you, Christian. And yeah, very impressive to take the question on the move. So the next
sorry for this. Just left the taxi and ended in the airport. So sorry for this.
Okay, it's okay. Very well done. The next question is for Keith and Rob, and it's from Ed Newman Sanders. So, at face value, the quantity of concrete in the building seems high to satisfy architectural aspiration. Is this the case? And if so, did the thermal mass of the exposed concrete surfaces help to offset the operational carbon against the embodied carbon?
I can probably answer that from the design point of view, I suppose. I guess the design of the building started probably 2015, and it went through a couple of different iterations where it had to go back to the drawing board. So certainly back then, embodied carbon wasn't quite as much of a focus as it is if we were starting the same project today. The focus of the project at that stage was achieving BREEAM outstanding, which in the design stage it has achieved. And I guess in BREEAM only a small portion is the actual structure and the structural materials involved. So there's while you can achieve BREEAM outstanding across a sort of holistic view of the building, the structure doesn't play as much of a part. In saying that, given the architectural aspirations, we managed to get quite a close column grid on the inside of the heart, and that meant that we had quite an efficient flat slab solution through the middle of the heart, and that was key in just making the structure more efficient generally. And then around the outside, although we had quite long spans, the hollow core gets quite a lot of efficiency because it actually has quite a big structural depth. So you can span long distances without actually as much concrete as, say, an in situ conventionally reinforced system where, the hollow core takes advantage of the stressing, pre-stressing to achieve those spans with kind of minimal volume to depth, volume to span ratio. So those sorts of things helped. If we were to design the building again today, I think we'd probably challenge the brief a bit more. We'd ask, do you need these long spans on the outside, the kind of flexibility that you need? Can you still achieve that? But throw some columns in the middle of it and reduce the amount of transfers in the building. The main stability structure is a moment frame around the heart, as opposed to sort of a central core. Various reasons for that as the design progressed, but maybe if we were to do it again, we'd push for a more conventional kind of central core to the building. But it's very exposed visual concrete, limited finishes, so you kind of have to look at it in a holistic building point of view where the embodied carbon of the finishes is reduced.
Brilliant. No, thanks for that, Rob. Some great thoughts there, I think.
Okay.
Next question, we'll move on to you, Mike. We have a question from Ricardo Stroschio, who asks about New Storstrom Bridge. Assuming that the railway includes continuous welded rail, was there any particular challenge in relation to satisfying the track structure interaction criteria and the long viaduct with the cable stayed section?
Well, there's a simple answer to that, yes. It was pretty tricky. There were quite a lot of aspects to look at. The ones we had most trouble with were at the expansion joints, where we had to look very carefully. And that's part of the reason why we've got tie downs involved as well, and also shock transmission units involved as well, because between the various bits of the railway loading that we had to deal with and the deflection criteria, it was very tricky. There is also a requirement for runnability in the event of a ship impact. So that because it's such a long bridge, the client was aware that if there was a ship impact, they may not be able to close the railway line very quickly. And so you've got effectively a survivability criteria to make sure a train doesn't go off if it gets hit by a ship, which actually caused us perhaps more problems than most of the rest of it. So yeah, that's why there was some very detailed dynamic analysis done to prove that all this worked.
Okay, thank you very much, Mike. And Christian, come back to you. Just one more, and then we better let you go before you walk into something. How do you see the potential of using non-corroding tensile elements for external tendons in the near future?
let's say if there is a potential for this, I would say the best potential is, or the best idea is, using it in an external tenant first. Because if we think about non-corrosive materials, we talk about carbon or similar things, and there is of course limited long-term experience with these things. So we do not know what really happens 25, 30, 40 years in an alkalic milieu. So we do not know, for anchorages, is there special creep and so on to be considered. So I would say, seeing the chance that typically external tenants are replaceable, I would say, we if we want to try it in a real practice and really want to get with these materials, gain some long-term experience, then I would say it's now the right time to use them and try it. Maybe not as a 100% non-metallic one, but maybe say there are some bridges where we use 2-3 tendons or a certain percentage with these non-corrosive material. That would be, I would say, a nice trial, and I would say it's the right time to start it now. To say yes, in parallel to all the studies and testing and research that is done at the university, we could gain here really in practice interesting experience. There are some first projects with stay cables, for example, where one cable, for example, bridge in Maine in US, where this already was done. So far, with external tenant not started, would say we should, or it's a good timing now, would not recommend this for bonded tendons at the moment, because we really do not know enough about durability.
Okay, brilliant. Thank you ever so much, Christian, and safe travels, and thanks for everything.
Thanks, and sorry for leaving a little bit earlier.
That's okay. That's great. Thank you for staying as long as you managed to. I think we've probably got time for just one more question. Well, sorry, two more questions. Coming back to you, Rob and Keith. There was huge amounts of complexity there, obviously, but what do you think were the most challenging details to design and to construct, as it turned out? So maybe that's a sort of question for you, Rob, on the design, and Keith on the construction.
Sure, yeah. So we had kind of a mixture of materials and construction methodologies throughout the building, and often it would be where at the corner of that internal heart, you would have a moment resisting column and beam stability frame meeting in two directions, but then the hollow core had to change span directions at the corner as well. So you had a transfer beam for that coming into the one column. So you had an in situ slab on one side, hollow core on the other side, a transfer beam, two moment resisting frames, and then at level 4 we also had a large steel plate girder coming into the same interface, but cased in concrete. So those were the sorts of interfaces that were the really tricky things. And then, as we talked about at level 10, add some PT into the mix. Yeah, so those making that look architecturally good and simple looking on the outside and minimal was kind of the real challenge when all of the complexities on the inside of the surface.
Great, thank you. And anything you want to add, Keith?
Yeah, the whole project was pretty challenging, to be honest. It was, and bringing the kit of parts in, I'd say 80% of any interface between two different precast elements or other sort of elementized unit was pretty tricky. It looks fairly repetitive, the project, but when you get into the design and the load cases, there was quite a large number of different scenarios which we had to deal with. So it wasn't a case of designing something once and copy paste, although it looks like that from the outside. Actually, internally, it's actually quite a lot of complexity. So yeah, we spent many hours in meetings going backwards and forwards with manufacturing team, Rob and his team, the architect, trying to get the joint positions agreed and get the connections and the joints looking suitable and also working correctly. So yeah, the whole project was fairly challenging.
Yeah, tremendous. Thanks both. And I think just one last question. We'll cycle back round to you, Mike. One from the designers, I think. That cross section for Storstrom is obviously pretty asymmetric with that step in it for the railway. Was the fact that the sort of principal axes of the bridge kind of non-vertical and rotated, did that give any problems with the with making sure everything sort of remained in compression under the pre-stress?
Yes, we had a lot of fun with local axes and the directions, because you've got not only that, you've also got the curvature, which was interesting, should we say. There was a lot of time spent trying to work that out. But to be fair, the design that had been done up to that point we became involved was sufficient for us to enable us to develop it properly. So yeah, it was a challenge. It needed a lot of looking at. It is quite unusual and a lot of issues involved with it, but the deck team did spend a long time looking at it, and I think they managed to solve all of those problems.
Because usually there's always some sort of asymmetry that rotates, but it's usually so small.
Yeah, there's always something. Yeah, but with this,
it's
really quite big. And so you're looking very carefully at your delta frames and your diaphragms and the pre-stress and trying to get it all to work together. Plus, there were a few tricks played with the construction sequence to tweak the bending moments around, because it went up basically span by span and then it was made continuous. And there were a few tricks played with adjusting the levels before it was locked off, so that you get something closer to your continuous profile rather than you simply supported in the dead load. So yeah, lots of little tricks, but yes, it was hard work.
Brilliant. Well, thank you very much, all of you, for taking those questions and for your presentations. So that will close the Q&A. I'll just attempt just to quickly share my screen again, just to finish this off here. So yeah, thank you very much, everybody, for that. Now that brings us to the sort of the formal end of the main conference. I hope you enjoyed it. Just a couple of quick things just to finish with. So first of all, there will be a feedback form sent around to you fairly soon. So please, can I ask you to take the opportunity to complete that, because your comments, what you like, what went well, what would be even better if, suggestions for other topics to cover, they really do help us make future events as good as they can be. The session recordings today, they will be available to view on demand at the iStructEase website, but that will probably be early 2023 before they become available to others. And just finally, in closing, just wanted to draw your attention to the Structural Rehabilitation Conference that's shown up on the screen here. There is a discount code that can be used, and you can find that in the link in the resources tab next to ask a question. And with that, we are complete today. So again, thank you to all of our speakers. And with that, I would just thank you all very much again for joining us this afternoon, and wish you a very good evening. Thank you and goodbye.